So we're going to talk about tensor products. Now, when I first learned about tensor products, I kind of understood what a tensor product was, but when I tried to actually do calculations with them, I got stuck. I kind of knew about tensor products, but I wasn't comfortable working with them in a concrete way. So in this video, I'm going to go through the whole process of learning about tensor products, not just what is the definition, but also how do you actually work with these things. So we're going to start with constructing the tensor product explicitly, and from there we're going to go through a bunch of examples of doing calculations with those tensor products. Now I'm going to talk about tensor products of vector spaces in this video, but these ideas also generalize very easily to tensor products of modules over any commutative ring or even over a non-commutative ring with some slight modifications. So let's start with constructing the tensor product. Now when you think about constructing the tensor product, you can kind of think of it like sculpting a statue. When someone wants to sculpt a statue, they start with a big lump of stone that doesn't really look like the statue at all. And then they slowly chip away at it and refine it until they get that final form that they're interested in. We're going to do the same thing with a tensor product. We'll start with a huge vector space that doesn't really look like the tensor product, and then we'll add a few relations and extra equations to get us down to that final vector space that we really care about, the tensor product. So let's start with that huge vector space. We're going to define our huge vector space Z as the vector space with basis vectors E subscript V comma W for all elements V in V and elements W in W. So Z is going to have one basis vector for every pair of elements V and W. So Z is going to be a massive vector space because for every single element in that vector space V and every single element in that vector space W, we're going to have one basis vector. Now, instead of writing the basis vectors as E sub V comma W, I'm just going to denote this by V comma W, like that. So each of these is going to be a basis vector in Z. And because those are all basis vectors, we can write an arbitrary element of Z as the sum of some constants, C VW, times the basis vector V comma W. And we're going to define that we only take finite sums of these basis vectors. So because these are all basis vectors for Z, an arbitrary element of Z is going to be a linear combination of those basis vectors. Now right now, because these are all basis vectors, they are linearly independent. That's part of the definition of a basis. And what that means is that these V comma W terms don't have any relations between them. For example, if we look at the basis vectors 2V comma W and V comma W, if we add these together, there's no way to combine them because these are linearly independent vectors. They don't really have anything to do with each other. In order to take this vector space Z and get down to the tensor product that we really are interested in, we need to start adding relations between these different elements. So the key thing to realize about Z is that we can add relations between elements, and let's see how we could do that. Suppose that A and B are both elements of our vector space, and we want them to equal each other. We want to introduce this equation to the vector space. The way we do that is by considering the element A minus B. This is an element of the vector space, and we can take the span of this element. That gives us a subspace of the vector space containing all of the multiples of A minus B. And the way we add the relation A equals B is we consider the quotient Z mod the span of A minus B. So this quotient space has the property that anything in the span of A minus B is equal to 0. That's how the quotient works. So if we say C is some scalar, then C times A minus B is equal to 0. Or in other words, C times A equals C times B. So we get the relation A equals B that we're looking for. So this lets us add any equations that we want to the vector space. And in order to understand exactly how this works, let's look at a familiar example of constructing the direct sum of vector spaces. So our goal right now is to take this vector space Z and add relations using that quotient space method until we get the direct sum, V direct sum with W. Now, what are the relations that we expect in the vector space V direct sum W? There are two key relations. The first is if we take V1 comma W1 and we add V2 comma W2, we want to get the result V1 plus V2 comma W1 plus W2. So we want to be able to add the elements of V and the elements of W together to get one big result. The other thing we want is if lambda is some scalar, we want to have lambda times V comma W equals lambda V comma lambda W. These are the two relations that really get us down to the direct sum of these two vector spaces. So if we want to introduce these relations to our vector space, remember what we did just a little bit earlier. Instead of considering these as equations, we take the left side of the equation and we subtract the right side of the equation. And what we do is we take the vector space Z and we take the quotient by the span of these two vectors together. So the span of these two vectors is the set of all linear combinations of these two vectors. And if we do that, inside of this quotient space, this and that are equal. This and that are equal. So this, in fact, is the direct sum vector space. This is how we use relations to get vector spaces out of Z. Now, when we look at the span of these vectors, we're actually talking about the set of vectors that look like this for all possible values of V1, W1, V2, and W2. We take all of the possible 4 vectors we could put in here, and then we take the span of all of those together. And the quotient by that entire space is what gives us the direct sum. So as an example, let's consider the real numbers direct sum with itself. So this is going to be Z, defined the way we did earlier, mod the span of some real numbers, let's say A comma B plus C comma D minus A plus C comma B plus D. And then the second vector is lambda A comma B minus lambda A, lambda B. So inside of this direct sum, R direct sum with R, we could look at, for example, what is 2 comma 0 plus 3 comma 5. We know that one of the relations here is that 2 comma 0 plus 3 comma 5 is equal to 2 plus 3 comma 0 plus 5. So in the quotient space here, this is equal to 5 comma 5. And similarly, if we had something like pi times 1 comma 2, this is equal to, by the second relation, pi comma 2 pi. So in each case, we can take the numbers in these sums here, consider the relations where we plug in, for example, A equals 2, B equals 0, C equals 3, D equals 5. And that gives us, in the quotient space, a new answer for what that vector is going to look like as a result. Now, one of the reasons that this vector space is called the direct sum is that the rules that we have here, that we added to Z, are very similar to the rules for when we add vectors. For example, we have this relation down here, lambda times A comma B equals lambda A, lambda B. If we think about how this relates to addition, well, we have a rule when we're adding things that's called the distributive law. Lambda times A plus B equals lambda A plus lambda B. So we see that the relations for the direct sum mirror the relations for adding things. And the tensor product is similar, but instead of making the rules look like addition, we want to make the rules look like multiplication. So we want the tensor product to kind of look like we're multiplying vectors. Now when we talk about the tensor product, instead of denoting the vectors by ordered pairs, v comma w, we usually denote them by v tensor w. So we use this O times symbol between the two vectors. So an arbitrary element of z is going to look like the sum of c v comma w times v tensor w. This is the same thing as we saw for z earlier, except I'm just using a different notation for this v comma w part. Now let's think about the relations. What relations do we expect when we're multiplying numbers? Well, like we saw earlier, one of them is the distributive law. So a times b plus c should equal a times b plus a times c. And we can also do it on the other side. A plus b times c equals a times c plus b times c. So we want to take these relations and kind of port them over to the tensor product. So on that side, we'll have a tensor b plus c equals a tensor b plus a tensor c. And similarly, a plus b tensor c equals a tensor c plus b tensor c. Now we also need to think about scalar multiplication in this vector space. So what is lambda times a times b? One way that we can look at this is lambda a times b. And another way we can look at it is a times lambda b. This is the way that we expect scalar multiplication to work on a product of two elements. So if we look at the tensor product side, we're going to have the same kind of rules. Lambda times a tensor b should equal lambda a tensor b, and that should equal a tensor lambda b. So these relations are all set up to make the tensor product look like an actual product, look like multiplication. And these three relations are the ones that we're going to use to make that tensor product. V tensor w is equal to z mod the span of these three equations. So I'm going to go on the side and call these 1, 2, 3. And to make it nice and formal, remember that when we're doing these relations, we actually take the quotient by the left side of the equation minus the right side of the equation. So we'll do minus, minus here, and then over here, we'll have to split this into two parts. So we have lambda a tensor b minus lambda a tensor b, and also lambda a tensor b minus a tensor lambda b. So these are the final relations. So when we take the tensor product v tensor w, we take the quotient of z by the span of 1, 2, 3, and 4. Those four relations are the ones that we use to set up the tensor product. And this is our final construction. So this is our final definition of the tensor product. We've taken these relations that we know from multiplication and we've added them into the vector space using the fact that we can take the quotient space by the difference between the two sides of the equation to make that equation always true in this final tensor product. So just like that, we have sculpted the tensor product out of this huge vector space. So the elements of the vector space v tensor w are these finite linear combinations of the elements v tensor w for v and w elements of these two vector spaces. And we sometimes call these little things v tensor w pure tensors. So these pure tensors satisfy these equations that relate them to each other in the tensor product. Now we're going to go through a bunch of examples, and my goal here is to build a few key intuitions for how we do calculations with tensor products. The first key intuition I want to build here is the idea of pulling across scalars. So to see what I mean by that, let's take a look at this final equation here. Lambda times a tensor b equals lambda a tensor b equals A tensor lambda b. So what this equation is saying is if we have some scalar on the left side of a tensor, we can pull it across to the right side of the tensor. And that often gives us ways to simplify elements of the tensor product. So let's look at an example. Suppose that V is a vector space over the real numbers, and we take the tensor product of V with the real numbers. What does this tensor product look like? Well, let's think about a few examples just to kind of get a handle on what we're looking at. We remember that the elements of a tensor product are going to be linear combinations with these scalars times the pure tensors over here. So one example of that kind of element would be 2 times 3 tensor u plus 5 times 1 tensor v. So in this case, u and v are elements of this vector space over here. Now, we have to think about what we can do to pull across scalars to simplify these tensors over here. The first thing we know is that we can take the scalars on the outside and bring them over to this tensor on the right. 2 times 3 tensor u is equal to 3 tensor 2u. So we can do that to this first element over here. We can write this as 3 tensor 2u. And the same thing over here, 1 tensor 5v. But over here, we can write this 3 as 3 times 1. And 3, this 3 in the front here, is another scalar. It's another lambda. So what we're looking at here is lambda a tensor b. And we know again we can pull the lambda across to the right side. We can take this 3 and go over to the right. So I'm going to take this 3 and move it over to the right side. We're going to just be left with a 1 on the left. And on the right side of the tensor, we multiply 3 times 2u. 3 times 2u is 6u. And over here, we add 1 tensor 5v. And now take a look at this first equation up here. This equation says that if we have this same element a on the left side of the tensor, we can add the things on the right. Over here, we have a 1 on the left side of the tensor for both of these. We can add the things on the right. If we put those together, we get 1 tensor 6u plus 5v. So using these rules, it seems like no matter what we start with over here, we can always write it as 1 tensor some element of this vector space V. Let's see if we can do that in general. We want to kind of copy this same idea, but for an arbitrary element of R tensor V. So an arbitrary element of R tensor V, that's going to be this linear combination here of, let's say, C A comma V times A tensor V, where the elements A are real numbers and the elements V are vectors in this vector space. So the first thing I want to do is take this scalar C A comma V from the outside and pull it across to the right. We're going to take this CAV and over to the right. So if we do that, we're going to get A tensor C A comma V times V. And again, remember, we can write A as A times 1. This A is a scalar. I'm going to pull it over to the right side as well. So we get the sum of 1 tensor A times C A comma V times V. And finally, remember this rule up here. If we have the same vector on the left side of the tensor, we can add the things on the right. Over here we have a 1 on the left side of the tensor. We can add all of the things on the right in this sum. So this is equal to 1 tensor the sum of A, C, A comma V, V. So for any arbitrary element of R tensor V, we can write it as 1 tensor some element in this vector space V. And for that reason, this vector space is just isomorphic to V. So the idea of pulling across scalars is a very powerful way to simplify tensors. Now I want to look at another quick example before we get into the next key intuition to build. And that is, Let's suppose we're looking at the tensor product v tensor w. So we just have two arbitrary vector spaces v and w. The question is, what is v tensor 0? So this is the 0 element in the vector space w. Well, there are a few neat tricks we can use to figure out the value of v tensor 0. But before we do that, think about it intuitively. We want the tensor product to look like multiplication. So what is v times 0? Well, of course, that's just going to be 0. So we kind of expect this in the tensor product to be the 0 element. And in fact, we will show that that's the case. So the first thing I'm going to do is ask what happens if we take v tensor 0 and add v tensor w. Well, if we do that, remember, again, this first rule. If we have the same thing on the left side of the tensor, we add the things on the right. So this is equal to v tensor, the sum of these two things, 0 plus w. But by the definition of 0, we know that 0 plus w is the same thing as w. So this is just v tensor w. So if we take v tensor 0 and add v tensor w, we get v tensor w. So if we subtract v tensor w on both sides, we get v tensor 0 equals 0. I want to show a few other fun ways that we can play around with v tensor 0 using the rules of tensor products. The first is, we know that v tensor 0 is the same thing as v tensor 0 times 0, because this is just equal to 0. But 0 is a scalar, and we can pull the scalar across to the left side. So if we do that, we get 0v tensor 0. And so 0v is equal to 0, so this is 0 tensor 0. And we can prove this another way too, because v tensor 0 is also equal to v tensor 0 plus 0. So we can write that using the distributive law over here as v tensor 0 plus v tensor 0. Again, if we have the same thing on the left side of the tensor, we can add the things on the right. That's what we're doing here. So v tensor 0 is also equal to v tensor 0 plus itself. So we subtract on both sides, and we get that this is the 0 element of the vector space. One more fun way to prove this, v tensor 0 is the same thing as v tensor -1 plus 1. So again, we can use this distributive law, this first equation up here, to split this as v tensor -1 plus v tensor 1. But -1 is the same thing as -1 times 1. And so this is just a scalar times 1. We can pull the -1 to the outside like we do here in this equation. So I'm going to write this as we pull the -1 all the way out. It becomes negative v tensor 1. And so v tensor 0 is equal to v tensor 1 minus v tensor 1. And so of course this is just the 0 element once again. So I've already kind of been hinting at that second key intuition, which is the distributive law. And the reason I'm calling it that is that it's almost exactly the same as the distributive law for multiplication. Basically, you can distribute tensors in the exact same way that you would distribute products. A tensor b plus c equals a tensor b plus a tensor c. So what I want to do is look a little bit at the basis for a tensor product. So let's suppose we have our vector spaces v and w, and we have a basis for each of these. So the basis for v is going to be e1, e2, e3, dot, 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 all the way to em. And the basis for w is going to be f1, f2, f3, dot, 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 to fn. Now, what is an arbitrary element of v tensor w going to look like? Well, let's first look at the pure tensors, elements like this. We're going to have an element of v tensor with an element of w. Well, all the elements of v are linear combinations of the basis vectors. So we can write an element of v as c1 e1 plus c2 e2 plus dot 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 plus cm em. and then an arbitrary element of W, that's going to be a linear combination of these basis vectors. Say b1 f1 plus b2 f2 plus dot 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 bn fn. So at first it might seem kind of difficult to expand out this tensor. I mean, it looks kind of complicated. There's a lot of stuff going on. But remember, we have the distributive law. And if we take these two distributive rules and we expand them more and more, we apply them over and over again, we get that distributing tensors is exactly the same as distributing normal products. So what would you do if someone said expand C1 E1 plus C2 E2 plus dot 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 times B1 F1 plus B2 F2 plus dot dot dot? It's basically just foiling. So you start with the first terms on each side. C1 E1 tensor B1 F1. But we can do better than that because we know we can pull across scalars. We can take this C1 and B1 all the way to the outside. So we can write it as C1 B1 times E1 tensor F1. And after that, we look at these two terms. So we add C1 B2 E1 tensor F2. And we would go on and on and on, plus dot dot dot, and then all the way to the final term in that expansion, CMBN times EM tensor Fn. So every single pure tensor can be written like this. And even if we take an arbitrary linear combination with some lambda scalars on the outside times these pure tensors, it's just going to look the exact same, except in front of each of these pure tensors, it's going to look like sum of lambda plus sum of lambda, and so on. So every single time when we take a linear combination of elements in V tensor W, it's always going to be a linear combination of these things right here, the pure tensors EI tensor Fj. In other words, these pure tensors generate the tensor product V tensor W. If we have a basis for V and a basis for W, taking the pure tensors, where we put those two basis vectors together for all possible pairs, that gives us a generating set for the tensor product V tensor W, because we can always expand out this linear combination using the distributive law to get these pure tensors all by themselves. And it's a little more difficult to prove this part, but in fact, these tensors are also linearly independent, which means these pure tensors are a basis for V tensor W. So now we can answer the question, what's the dimension of V tensor W? Well, the dimension is the same thing as the size of a basis. So what is the size of this basis consisting of EI tensor Fj? Well, the number of possible pairs where we pick one thing from the basis for V and one thing from the basis for W is the size of the basis of V times the size of the basis of W. And that's the same thing as the dimension of V times the dimension of W. And that kind of agrees nicely with the fact that we call it a tensor product. All right, time for more examples, more examples. The first thing we're going to look at here is R2 tensor R2. How can we write an arbitrary element of this? Well, we know that the pure tensors are going to be AB tensor CD. These are just elements of R2. And we can write each of these vectors in a simpler way, because we can write AB as A times 1, 0 plus B times 0, 1. And we can write CD as C times 1, 0 plus D times 0, 1. And just like we said before, we can expand this out using the distributive law. So first, we just have to FOIL this. A times 1, 0 tensor C times 1, 0 is going to give us AC times 1, 0 tensor 1, 0. And you might ask, where is this scalar exactly? Am I saying we take AC times 1, 0 and then tensor that with 1, 0? Or am I saying this is the tensor and AC is a scalar out in front, like here? The answer is, it doesn't really matter, because lambda times A tensor B is the same thing as lambda A tensor B. They're equal to each other. So a lot of times when people are doing tensor products, they won't bother to write parentheses on the outside or on the inside because those two expressions are exactly equal to each other. So I'm going to drop the parentheses right now to make the notation simpler. After that, if we keep foiling, multiply these two terms together, we get AD times 1, 0, tensor 0, 1. We multiply the inside terms, we're going to get BC times 0, 1, tensor 1, 0. And then finally, these last two terms, we get BD 0, 1, tensor 0, 1. Now it's important to keep in mind when we're doing the tensor product that A tensor B is not equal to B tensor A. We're not allowed to switch the order of elements in a tensor. We have to keep them how they are. We're allowed to pull across the scalars, but we can't switch the vectors. So, for example, when we take B01 tensor C10, we do have to leave it as BC01 tensor 10, because that's the order they appeared in the original tensor up here as well. So what we've shown here is any tensor in R2 tensor R2, we can expand it out as a linear combination of these four tensors here. 1, 0 tensor 1, 0, 1, 0 tensor 0, 1, 0, 1 tensor 1, 0, and 0, 1 tensor 0, 1. So like we were looking at earlier with the basis for an arbitrary tensor product, these pure tensors here are going to be a basis for R2 tensor R2, meaning the dimension of that tensor product is 4. I want to look at one other way that we could write elements of R2 tensor R2. So let's say we have AB tensor CD. What I'm going to do is I'm going to leave CD the way it is, and I'm just going to distribute out AB. So we can write AB again as A10 plus B01. And this is tensor CD. Now if we distribute this out, we're going to get A times 10 tensor CD plus B times 01 tensor CD. So we've only distributed on the left side and left the right side exactly how it is. Now we have these scalars in the front still, A and B. But remember, we can pull across scalars. So I'm going to pull these to the other side, and even more than that, I'm going to multiply them into the vector. So I'm going to take A times CD, and that's going to give us AC, AD. And same thing over here, we're going to have BC, BD. And that is going to mean that the tensors on the left side are just 1, 0, and 0, 1. So what we've just shown is that we can write an arbitrary element of R2 tensor R2 as 1, 0 tensor a vector in R2 plus 0, 1 tensor a vector in R2. So it kind of seems like R2 tensor R2 is really just two copies of R2. One of them corresponding to this left tensor 1, 0, and one of them for this left tensor 0, 1. So this is another way that we can write arbitrary elements of a tensor product. And which way is preferred for writing those elements is going to depend on the application. What exactly are we trying to do with those tensor products? More generally, let's look at the tensor product R3 tensor V for V some arbitrary vector space. Just like before, we'll look at the pure tensors, and we know that any element of the tensor product will be a linear combination of those pure tensors. So a pure tensor in R3 tensor V is going to look like the vector ABC tensor some vector V in that vector space. Now we can write ABC as A times 1, 0, 0 plus B times 0, 1, 0 plus C times 0, 0, 1. So now we can expand this out using the distributive law, the second one here. So if we do that, we're going to get, for this first part, 1, 0, 0 tensor AV. Remember, we can pull the constant, pull the scalar across to the right side. Plus, for this second part, we'll have 0, 1, 0 tensor BV. Again, I've pulled the B across to the right side. And finally, plus 0, 0, 1 tensor CV. So again, we can write any pure tensor in R3 tensor V as 1, 0, 0 tensor something plus 0, 1, 0 tensor something plus 0, 0, 1 tensor something. And if we take a linear combination of elements that look like this, we can use this first distributive law here to combine all of the 1, 0, 0 parts. So any arbitrary element in R3 tensor V is going to look like 1, 0, 0 tensor something plus 0, 1, 0 tensor something plus 0, 0, 1 tensor something. We're always going to be able to split up the tensor product in this way. And for that reason, R3 tensor V as a vector space is isomorphic to V3, because we just have 3 different copies of V corresponding to the 3 basis vectors in R3. And you might remember we saw earlier that R tensor V is isomorphic to V. So it makes sense when the exponent is 3, the exponent over here is also 3. So the pattern matches. And in general, by the same basis argument, Rn tensor V is isomorphic to V to the n. So just like the direct sum lets us combine 2 vector spaces in a way that works like addition, the tensor product lets us combine 2 vector spaces in a way that works like multiplication. The 2 key intuitions to have when we're manipulating elements of a tensor product are that we can pull across scalars. So if a scalar is on the left side, we can always bring it over to the right. And the distributive law, which means we can FOIL out tensors in a similar way to how we FOIL out products of ordinary numbers. So that's how we can deal with elements of a tensor product.